So our next speaker is Mukund Rangamani, who's going to tell us about looking at extremal black holes from very far away.
Thank you, Shreya, and thank you to the organizers for inviting me back to ICTS. It's been great. So indeed, I'll tell you about something that's ongoing and hopefully should come out soon with an excellent postdoc at Santa Barbara, Maciej Kolanowski, who is primarily responsible for much of these insights. And I'm going to tell you my student Ilya Rakic and Joaquin Turiachi, who's at Seattle. Okay, so let's get to it. Context is non-supersymmetric extremal black holes in semi-classical gravity, which, as one knows, they exist and they appear at the leading order in 1/g Newton to have non-zero entropy at zero temperature. This is a priori problematic with respect to the third law, but that by itself is not an issue. What's more of an issue, which was pointed out nearly 2.5 decades ago, three and a half decades ago, was that this non-trivial entropy at zero temperature poses a problem for how non-extremal black holes near extremality Hawking radiate. If you look at the departures away from extremality, the energy departs quadratically, whereas entropy departs linearly, and that says that at low enough temperatures, you don't have enough energy to even emit a single Hawking quantum, as Sandip and friends showed way back in the 90s. There have been various attempts to resolve this puzzle. There have been various proposals over the years, but the final answer turns out to be quite prosaic, and one which has been understood in the last 4 or 5 years, which says that this semi-classical intuition is somewhat illusory, that actually extremal black holes are like ordinary quantum systems with very few low-lying excitations. And the way this came about was by analyzing the semi-classical connections to the extremal black hole entropy, in particular realizing that if you're trying to evaluate the gravitational path integral by saddle point, there's a saddle point answer, but there's also a one-loop determinant. And this one-loop determinant needs to be evaluated with care in the context of near extremal black holes because quantum corrections are amplified in this region. So schematically, the answer looks something like this. The partition function has a usual semi-classical formula, which is exponential of the Bekenstein-Hawking entropy, S0. There's a linear deviation from it. There's a logarithmic correction in the area that Ashok, for example, famously pioneered the study of about 15 years ago. But the new feature is that if you actually calculate, this piece also comes from one loop determinant, but in particular, there's an additional piece in the context of near extremal black holes, which is temperature dependent Pawel law correction as a prefactor to the semi-classical answer. The one loop determinant scales as a positive power of temperature. Okay, and this arises because there are nearly gapless, in the extremal case, there are gapless modes localized in the near horizon, which are strongly coupled and need to be treated quantum mechanically. The zero mode contribution which leads to this temperature dependent correction can be isolated by examining how these modes behave in the near horizon region. So there have been various ways people have thought about this, but one is the fastest way I know is to basically appeal to the fact that extremal black holes have a near horizon, which is an area through throat, so it has an enhanced SL2R isometry, and you can sort of dimensionally reduce down to this area space-time and use an effective JT gravity description. Classically, this was worked out in some papers by Sandip and his collaborators. And then on top of that, you can start doing quantum effects. Alternately, you can just work in a full near extremal geometry and deduce that the spectrum of quadratic fluctuation operator has low-lying zero modes. And I would argue that this latter perspective is already slightly the right thing to do in the case of axisymmetric solutions where the dimensional reduction to ADS2 is contingent on using an ansatz that's not necessarily consistent. So for example, this is something that we did last year, and also some other group at Harvard did similar things. Yeah?
You're saying if you just did the dimensional reduction in the spinning case, it doesn't quite work out.
I mean, the dimensional reduction is contingent on putting an ansatz which is not well posed.
You can do an alternate anyway. You don't have to have an exact S2. You can just have the S2.
No, the point is not so much, it's not an S2. The fact that the ADS2 is warped. The warping has to be accounted for. Yeah. and the answers assume that the warping is not affected under dimension reduction. This to me is not meaningful thing to do. The warp factor needs to be allowed to be a dynamical feature. No, that's not true. So it's not relevant to what I'm going to say because I'm going to do something else. So, okay. So all of these analyses, broadly speaking, just zoom into the near horizon and just use the ADS to. And once one identifies the zero modes, you can sort of use a small temperature regulator, still be staying with the near horizon region, figure out how these modes get gapped as a function of temperature, and then compute the determinant. Can we do better? Can we provide a perspective on this problem by not zooming into the near horizon? Can we just stick with the entire space-time and ask what's actually happening? And that's really what the question I'm going to try to answer. To be clear, I want to distinguish what I'm going to say with two important features that have already cropped up. The idea is not to use the ADS2 at all. Okay? So for example, the original calculation that was done by Ilyasov and Tadashi, they use a semi-holographic language. They basically worked in the near zone, in the near horizon region, and the far zone, and evaluated determinant by sort of patching things together. Likewise, it's very different from what you probably heard from Ashok on Monday, where if you want to compute indices in supersymmetric black holes, you can do them by working in the full space-time, by working with a suitable complex Euclidean saddle and tuning a particular value of chemical potential. And there the index calculation picks out a saddle, which in that case doesn't even necessarily have an ADS2 throat, but compute correctly reproduces microscopic counting. Okay? I'll make two claims and I'll justify them in the rest of the talk. Claim number one is that the near horizon zero modes lift to off-shell modes of the quadratic fluctuation operator around the near extremal black hole. And these off-shell modes are such that their eigenvalues scale with the Matsubara frequency of the Euclidean problem. The modes come in various categories. Almost universally, there is a class of modes associated with what I'm going to call the Schwarzian modes that's responsible for sort of the graviton fluctuations in the ADS2 throat. There are other modes, light modes in the problem, which arise which depend on the details. They could arise from isometries of the background geometry. Your background could be spherically symmetric or axisymmetric, and in either case, you'll either get non-abelian or abelian zero modes, families of zero modes associated with those isometries. Or you could have gauge fields that are sourcing the geometry, or probe gauge fields in the geometry, and those would additionally give a family of such light modes. Okay? And we'll see examples of all of these in the course of the talk. The second claim is something slightly technical, something that showed up in my discussion last year with Joaquin and Ilya, which is we noticed that if we were trying to find the zero modes in the near horizon geometry of the curved black hole, then there's an expectation that associated with axisymmetric azimuthal killing field, there is a zero mode in the geometry. We couldn't find one that was smooth in a particular gauge choice. Okay? And we sort of posited this as a potential issue for other near horizon computations. I'm going to give you a simple resolution, namely that in vacuum, in Ricci flat geometries, harmonic gauge is usually used, is just bad, and I'll show you why. Okay, so this is the outline of my talk. So I'm going to sort of show you first the simplest possible example of how this works by demonstrating analytically a class of eigenmodes in the near extremal BTZ geometry. The second part, and then I'll show you some numerical evidence for Raster-Nordstrom black holes in ADS, and then discuss the issue about gauge choices in Ricci flat geometries. The last two pieces involve basically contrasting what happens in the near horizon versus full geometry, and what ensembles one is supposed to work with, what boundary conditions one is supposed to work with, etc. Some of which are known to the experts, but I'm just going to sort of highlight it for completeness, and then tell you something about when certain modes may exist in the near horizon, but may not contribute to the one loop determinant.
You're completely working in Euclidean space?
Correct.
Will you make comments on the relationship between this and Lorentzian modes or polynomial modes?
Till at the very end. Okay. So if you tune out, come back then. I'll wake you up. Okay. So first exhibit, BTZ. So just 3D gravity with negative cosmological constant, no matter. I'll fix the thermal period asymptotically. and introduce a chemical potential for rotation along the spatial circle. Okay? And the saddle point configuration with these boundary conditions is the BTC geometry in Euclidean signature, as Shiraz anticipated, with imaginary rotation. Okay. So R plus and R minus are just the inner and outer horizon radii in Lorentz signature. And I've written down the physical parameters in terms of R plus and R minus, the temperature and angular velocity, and the mass and angular moment. It's useful to think about this problem slightly differently by combining the temperature and angular velocity into a left and right temperature from in light cone directions in the boundary. And so the limit I'm going to study is one where the left temperature is going to be very, very small, and that's going to give me a nearly extremal rotating BTC black hole. If I send the left temperature to 0, that will be the extremal. What do we want to do? So I want to study the spectrum of fluctuations around this geometry, and I just look for perturbations of spin 2 fields before people like me jump up and say, you're in ADS3, there are no spin 2 degrees of freedom. I'm going to gauge fix, and I'm going to study the modes in a particular gauge. So they will. So of course, it's true that the modes can be always chosen to be boundary gravitons, but you can always also choose to represent them in other gauges by providing profiles for spin 2 fields in bulk. Okay, so H mu nu is the fluctuation, and sometimes I'll use it with a tilde to sort of talk about partially trace removed object. The quadratic perturbation, if you yes,
this gauge choice corresponds to like somehow fixing the asymptotic boundary so that there are no boundary gravitons, but I mean, what could you say a little bit more?
What can I say again? So what I'm going to do is I'm going to basically, just like if you, for example, imagine doing Maxwell theory, I'm just going to put in the Lorentz gauge condition and just look for solutions, including the Lorentz gauge term. Right? So it depends on what gauge fixing function I use. So in this case, I'm going to stick in this harmonic gauge fixing term, and then the quadratic fluctuation operator now cares about this gauge fixing term. Right? So you could choose to work with some other gauge fixing term and work with physical gravitons. Then all the modes are really at the boundary. They're not anywhere in the boundary. So once I've done this, there's also a ghost action with a kinetic term, which is basically given by that operator. Okay? So the trick I'm going to try to play for now is I'm going to sort of focus primarily on looking at this guy so that I can isolate the physical, the modes without having to worry about the gravitons, without having to worry about the ghosts. Okay? So I'm just looking at physical fluctuations. So there'll be transverse traceless spin 2 excitations of the gravitons. The quadratic, so if you use this gauge fixing term and this Einstein-Hilbert action, you can convince yourself with a little bit of work that the Einstein-Hilbert, the quadratic operator that you care about is this Lichnerowitz operator, which cares about just some spin 2 Laplacian plus contributions from background. In ADS3, this is, since it's maximally symmetric, all of these things basically give you some mass term for the gravity. So in the near horizon, what do we expect? So we have an ADS2 fibered over a circle. The circle has constant size. So we expect a set of 0 modes associated with the asymptotics of ADS2, the sort of the JT gravity modes, the Schwarzian 0 modes, and they are in the kernel of the spin 2 Lichnerowitz operator of the near horizon geometry. Okay, I just rephrase my question again. We want to know what do these modes look like in the full space-time. So we just solve for the modes. We just look for eigenmodes of that quadratic fluctuation operator, subject to conditions that the metric fluctuations are transverse and traceless, physical gravitons. I'm not going to try to go through it in real time, just tell you that here is an exact analytic set of formulas for any TL and TR for these modes. Okay? And we solve for them, but they actually exist in the literature. If you stare hard enough, Justin and Shobik worked it out, and it's also used in some paper by Alejandro Castro and friends 5-6 years ago.
Question?
Yeah.
I'm a little confused by what you mean by the solution in the full space-time, because typically I would say that the near horizon and the far horizon geometries are disconnected from each other in the extremal limit.
They're not really, right? I mean, you can scale in, but you don't have to.
You can what?
You can zoom in, but you don't have to.
But I mean, in the strict extremal limit.
It's true that it's infinitely far away. There's infinite proper distance from the boundary.
Right. So what does it mean to have a solution to? I mean, it sounds like you're specifying boundary conditions at the bifurcation surface, and then.
No. I'm realize that I'm first of all slightly away from extremality. I have a regulator. Right? So I'm going to look at the near extremal solution, right? And So TL and TR are not 0. But you can see there are modes whose eigenvalues at small TL scale linearly with TL. Okay? So at this point, it's just a solution to the full quadratic fluctuation operator in the full geometry. So it's not just we have the eigenvalues, we have the eigenfunctions. They have elementary functions. I'm just not going to show you them. And they just have some profile in the radial direction, and they are basically expanded in Matsubara modes in time. But what I will show you is how the modes behave as I lower the temperature. I'll plot roughly the norm of the modes with respect to the ultra local measure and ask where is the norm concentrated, where is the wave function norm concentrated. And I'm plotting it as a function of proper distance from the horizon, and this will answer your question, John. As you lower the temperature, the modes recede further and further down the throat. So norm concentrates closer and closer to the horizon at lower and lower temperature.
Is it that tells you that these are the right modes in the near extremal solution to become the 0 modes in the extremal solution? Yeah.
For one, because their eigenvalues scale linearly with temperature, they clearly become on-shell 0 modes in the extremal solution.
But there's no other solutions that would sort of enter the kernel as you go to...
In this case, we can check and see that it's not true.
Got it.
Of course, that's the advantage of that's why I'm presenting this example, because this has all the advantages of being analytic. Okay, you can do something more. You can actually take the wave functions, take the extremal limit, and see that they become the Schwarzian mode in the extremal limit. And then you can usually do what you were thinking earlier, which is to scale down the solution to the near horizon, and you see the profiles match function to function. Okay, but what I want to emphasize is that these modes exist as a function of Matsubara frequency for all values except 0 plus minus 1. And they don't exist for 0 plus minus 1 because those modes are not normalizable with respect to the ultra local. Upshot, you have eigenfunctions of the quadratic fluctuation operator with eigenvalues which whose eigenvalues at low temperatures scale linearly with the Matsubara frequency. If you just take this class of modes and compute their contribution to the one loop determinant, you will reproduce the Schwarzian contribution on the nose. Yeah. So therefore, we have evidence that we have actually identified the right set of modes. They have the right answer for the determinant. They give you their profiles are concentrated in the horizon. But I'm not doing anything with JT here.
No, I know, but in the end, since you get the result from the plot.
I never said the JT answer was wrong. I just said your ansatz for dimensional reduction was wrong for rotating black holes. And BTC is special because BTC is not warped.
But there is an ADS2.
There may be an ADS2, but you can't just reduce to 2 dimensions if you have ADS2 warped over some internal base space. No, but that's not a consistent ansatz. You can check that this answer is actually consistent with the CFT calculation that was done. In fact, that was the first calculation done by Ghosh, Maximilian, and Tadashi. I'll come back to a point here which I'm going to elide for now. The near horizon does predict that there's another 0 mode associated with the rotation. And I'll explain why that doesn't contribute from this perspective at the end of the talk. Okay. So having done some analytic work, let me show you what actually happens in something a bit more realistic, which is Wright-Nordstrom. And for simplicity, I'll use Wright-Nordstrom ADS because ADS provides a nice IR cutoff, so one can sort of actually find eigenmodes with nice Dirichlet boundary conditions for all the fields. So what we have is 4D Einstein-Maxwell with cosmological constant, and I'm going to look at electrically charged Wright-Nordstrom black hole, parameterized by a mass and a charge, and Maxwell potential. What do we expect? We expect Schwarzian 0 modes here because the near horizon is ADS2 times S2, the extremal limit. So we expect a set of modes from the Schwarzian. We expect a set of 0 modes from the U1 gauge field associated with large gauge transformations in the near horizon. And we expect an SO3 non-abelian set of 0 modes associated with rotations of the transverse S2. Now this turns out to be a slightly more involved example to work with for various reasons. The 0th order reason is nobody has, to date, very cleanly worked out the rules for computing the quadratic fluctuation operator with self-adjoint extensions in Einstein-Maxwell theory. something we had to do, something that Maciek did as part of this analysis. So you need to do work because both photons and gravitons are coupled in this background. And secondly, as is well known, the Einstein-Hilbert Einstein action is not sign definite in Euclidean signature. In Einstein-Hilbert, this problem is easy to deal with because the mode that's not sign definite is a trace mode. So the usual logic going back to Gibbons, Hawking, and Perry is to Wick rotate the conformal mode into the imaginary direction and then obtain a positive definite functional to work with. As I said, today, nobody's done this for Einstein-Maxwell because of these two issues. And our proposal is to integrate the Maxwell field in the imaginary direction. I should point out this nice set of papers by Don and Jorge Santos and Don's student, Xiaoyi Liu, who sort of have highlighted some of these issues in the last couple of years, context of Euclidean quantum gravity. And so we use some of their intuition to sort of construct how a quadratic fluctuation operator that actually has a sensible self-adjoint operator, so we can find eigenspectrum. We had to do something more. So we could pick any gauge we want. We could have picked harmonic gauge for metric, we could have picked Lorentz gauge for gauge fields. But at the end of the day, you have to ensure the fluctuations are physical. I would like to make sure that the metric fluctuations are transverse and traceless. If not, I have to do something more. I actually have to work out what the spectrum, eigenspectrum of the ghost operators is. And you'll see why that's important later. So we'll just work with a physical gauge choice. We found a gauge choice that seems to work. We'll use this gauge fixing functional for the metric and use the Lorentz gauge choice for the gauge field. And then working in symmetry sectors, we just obtain self-adjoint extensions for the quadratic fluctuation operators, which we diagonalize. Can't do this analytically, but we have Maciek who can do this numerically. So I'm just going to show you plots. So this is the first set of modes in the spherically symmetric sector. So I'm plotting on the horizontal axis temperature and the vertical axis the eigenvalue. And the point of these most boring plots, but they're very impressive, is to show you linear growth of the eigenvalues at low temperatures as a function. And the fact that these eigenvalues, furthermore, the last plot shows that these eigenvalues collapse, that they actually scale linearly with the Matsubara mode number. So in this case, I have eigenvalues which scale like n times t, for n being 2, 3, plus minus 2, plus minus 3, etc. So these are the lowest eigenvalues in the spherically symmetric sector. And you can roughly think of them as the primarily supported by the gravitons. But of course, the gravitons mix with the photons, so you can ask where are the gauge modes. And they turn out to be the next lowest eigenvalues in the spherically symmetric sector. But now they exist from n equals 1 onwards, not from n equals 2. The n equals 1 mode is now normalizable. Okay? And same set of conventions, the plot still shows the collapse, and you see the linear scaling. And finally, in the axisymmetric sector, we have a third set of modes. I'm just plotting here the m equals 0, l equals 1 harmonic on the S2, but the modes live in an SO3 irrep. So you can again see that there's modes with eigenvalues scaling linearly. So all told, we have in all these cases some, and in the latter case, which is what I have the plot for, the modes again localize beautifully in the horizon. So I can again look at the norm of the operators and look at how they concentrate near the horizon as a function of proper distance, or I can sort of look at the norm scaled by its density and look at the norm density, and again, it's sort of localized very much close to the horizon. So all of these say that the quadratic fluctuation operators around near extremal Rice-Nordstrom does indeed support a set of low-lying modes with eigenvalues scaling linearly with the Matsubara frequency. And that's sufficient to conclude that from each of these sectors that you'll get some contribution which is a number times log t over tq to the one loop, logarithm of the one loop partition function to the free energy. So you get a 3/2 from the Schwarzian because you're missing 0 plus minus 1 modes. You get 3 modes from the SO3, so that you get 3/2 from the rotation, and then you get a half from the gauge U1. And this is indeed the correct expected behavior in the grand canonical ensemble because we're fixing the chemical potential at infinity for both rotation and for the gauge fields. But it's not the full answer. To get the full answer in the grand canonical ensemble, one has to sum over shifts of the chemical potential by integral amounts because we maintain charge integrality. And each of these shifts would lead to new saddles, which themselves will have a saddle point answer. The Bekenstein-Hawking entropy will care about what chemical potentials I've put in. But the one loop determinant around all of them will have the same structure. If you finish this calculation and then do the Legendre transform to the microcanonical ensemble, there's a near horizon analysis which suggests that the final contribution only comes from the Schwarzian zero mode, i.e. the answer is basically 3/2 log T in the microcanonical ensemble. So in the canonical ensemble, I should have said canonical, it's not the microcanonical, it's at fixed temperature and fixed charges. Okay. Apologize for that typo. All right, yes, Ashok. I haven't checked, so I don't know, because in this case, because you have to turn on chemical potential, it's not obvious to me that they don't back react. So it's not clear that they don't give same order in 1 over G Newton, or whether they're suppressed. If you are suppressed, I think I agree with you, but there are examples like, as you probably know in the supersymmetric case, where the saddles have very different weights, but then multiple saddles combine to sort of work out correctly to give you the temperature dependence. So which is why I'm hesitant to actually make a strong statement. It would be good to understand, at least in one of these examples, what the other saddles do. I haven't done it. So. Okay, so that's my exhibits for the showing you how the modes extend off the near horizon region to the full geometry. We did one more example, but which I'm not going to show you. We did the hyperbolic ADS black hole, which was simpler because it doesn't have gauge fields. It doesn't have, it's just the Einstein-Hilbert theory, but I won't, plots look very similar, so I won't show you them. Let me then turn to the other issue that I was mentioning, which is about rotational zero modes. And the rest of the talk is going to be about these rotational zero modes, which has bothered me for about a year. Okay, so when we looked at the curved black hole, and we looked at the near extremal limit, and so we looked at the near horizon geometry in the near extremal limit, and we started asking what the zero modes are at extremality. So we found the Schwarzian zero mode very easily as an element of the kernel of the Lichtenowitz operator. But we expected, since his curve is a solution to Einstein-Hilbert theory, there should be another mode associated with rotations along the azimuthal direction. Picked an ansatz, and so the ansatz was basically some function along in the radial and temporal directions times given by a vector field, which is basically the azimuthal rotation killing field, and then you perform a diffeo along this vector field. So this is a large diffeo, so in the ADS2 region, so you expect that this gives you something non-trivial. What we found was that this mode, since it's a diffeo, you expect it to be a zero mode, but we found that, first of all, it doesn't satisfy harmonic gauge condition, and if you try to force it to satisfy the harmonic gauge condition, the mode is singular at the poles of the sphere. In some early part of this work, we decided, okay, we should try to check whether that was a peculiarity of Kerr and whether it persists for other black holes in 4 dimensions. So we looked at Kerr ADS and Kerr Newman, and in both these cases, somewhat surprisingly to me, we actually found a zero mode within the harmonic gauge choice. So this is not something we had done last year, but when we did it, we managed to find them. And the issue in the case of Kerr is just breakdown of harmonic gauge. And I'll explain why it breaks down in the following. So the harmonic gauge fixing functional is basically this trace divergence of this trace removed metric fluctuation. And as I said, a zero mode exists if it's generated by large diffeomorphism, which additionally satisfies the gauge condition. Then it's guaranteed to be a zero mode. A diffeomorphism doesn't change the Einstein-Hilbert part, and then if it doesn't change the gauge fixing part, it's obviously in the kernel of the quadratic fluctuation operator. So the Schwarzian, that's how we found it, but it's not so for the rotational zero mode, which, as I said, is generated by this killing field. And the reason that doesn't work is that if you try to compensate this vector field by a small diffeomorphism to bring it back to harmonic gauge, you find that you have to satisfy, the small diffeomorphism has to satisfy some elliptic equation. I'd like you to contrast this operator with an operator I showed you in passing. So the fact that the claim that there's no smooth solution amounts to the claim that this operator has a non-zero kernel. And if this operator has a non-zero kernel, it follows that the ghosts have 0 modes. Okay? For Ricci flat backgrounds like Kerr, this term is not there. So the operator is just the scalar, the spin 2 Laplacian. Sorry, spin 1 Laplacian because it's acting on vectors. And it's very easy to construct a 0 mode for the spin 1 Laplacian using eigenmodes of the spin 0 Laplacian. Therefore, for Ricci flat backgrounds, the choice of harmonic gauge to work out what happens for either in the near extremal or in the entire geometry is going to be problematic. And this is not a problem for Kerr, it's also a problem for solutions that Rob and Malcolm Perry wrote down in their Myers-Perry solutions in higher dimensions. So it persists for all Ricci flat rotating black holes, but thankfully it doesn't affect solutions like BMPV, which was something that bothered us after talking to Ashok, because there one can indeed find 0 modes while remaining harmonic gauge. So this resolves this technical puzzle that we had from our work last year. Let me, in the last 5 minutes, comment a little bit on ensemble choices, which will then finally lead me to a discussion in the BTC case. So I have presented 2 pictures. One, which is the old story, where people look at near horizon geometries, use some JT gravity-like intuition to compute determinants, or maybe just work at the full higher dimensional geometry. And the full geometry picture, where you sort of study fluctuations of the quadratic fluctuation operator in the entire space. The calculations are carried out in different ensembles, and they should be compared without care. If you're in the ADS2 geometry spacetime, if you're sort of truncating yourself down to this ADS2, whether you're in 2 dimensions after reduction, or if you're just in the full spacetime but you have an ADS2 part, the ADS2 asymptotics require that we fix physical charges and not their holonomies. Okay, so this is something that Ashok pointed out in the context of entropy functionals long time ago. But the logic is very simple. If you think of a Maxwell field in ADS2, the linearized solutions are constant and linear in the radial direction as you go to the boundary, and it makes no sense to fix the constant when the linear is growing. So the non-normalizable mode is the linear mode, and you fix the linear mode, but the coefficient of linear mode is the charge. If you're in higher dimensions, and I intentionally put d greater than 4 here, then you fix the chemical potential and not the charge. Chemical potential is the slow fall off, the charge is the fast fall off. You have a bit of wiggle room in 4 dimensions where you can do either, as these guys pointed out, or actually what Edward Witten pointed out in his earlier paper. But in 3 and lower, and therefore ADS2, you don't get to fix the chemical potential, you only get to fix charges. In the near horizon, the 0 modes only exist in the canonical ensemble, in the fixed charge ensemble. You can show that the modes you construct do not satisfy any other boundary condition. And the modes I displayed to you in the full geometry only exist in the fixed holonomy ensemble in the full geometry. Among these modes, the Schwarzian mode is universal. It's the one thing that doesn't, it's a pure energy mode from the point of view of either the near horizon or the full spacetime. It doesn't care about what your charges are, what rotations you have, and so on. So this contribution is something that's robust. But the contribution of all these other things, the gauge modes, the rotation modes, you have to calculate them with care. In the regulated near horizon geometry, you might calculate them infer that they exist by working in the canonical ensemble. But for technical reasons, people have computed their contribution to the one loop determinant by passing to the fixed holonomy ensemble, doing the sum over shifts, which can be done in the ADS2, and then Legendre transforming back. Okay, I don't find this satisfactory, but that's something that I think would be nice to clean up in the literature. It's having done this that people make the claim that the contribution in the fixed charge ensemble is temperature independent, and therefore in the fixed charge ensemble you only get a T to the 3 halves. Okay? I just want to highlight this because this is a subtlety that's mostly glossed over in much of this discussion, known to the experts but not sort of widely acknowledged. Okay, so finally, let me say something about BTC. So, yeah.
So the way to really fix this issue, you say, is to investigate whether, say, if you did the calculation in the asymptotically ADS of flat case, the Legendre transform involved going over to the fixed charge case is indeed correct.
Correct. Yes. Because you see, although every saddle gives you some power of temperature, the sum over the shifts might itself give you some other remove that power of temperature after some Poisson-Riemann summation. This is typically what happens in examples, but it's not something that's been worked out in every case. Okay, so in the last few minutes, let me just say something about BTZ. As I said, okay, the near horizon in this case is simple. It's ADS to really only fibered over a circle. It's not warped. If you want, you can dimensionally reduce. There is a zero mode associated with rotations. In fact, this is the zero mode. Now we are in a bit of a soup. We have one too many zero modes. We have the Schwarzian mode, which I already talked about, both in the near horizon and the far region, and the full geometry. In addition, we have a mode associated with rotation. But if this mode exists, it would predict that in the grand canonical ensemble, before summing over shifts, I would predict a factor of t squared. 1 abelian mode, so t to the 3 halves from the Schwarzian, and a t to the half from this guy. But you can actually go and check from the dual CFT what the answer is. In this case, you have that luxury. The answer is t to the 3 halves ensemble independent. Okay? And I won't go through this. This is the calculation that's nicely reported in this beautiful paper of Ghosh, Maximilian, Turiachi. But the point is you just start with the CFT partition function expanded in characters, and the answer comes out of this vacuum character if you assume a twist gap. And you can see that the answer, I've written the answer here in find the full answer in the canonical ensemble, but you can check that if you Legendre transform, the power of t doesn't change. So I have assumed that when I have a zero mode in the near horizon, I can regulate it by turning on temperature. That may or may not be true. It depends on what the thermal scale at which these modes are activated. It depends on their coupling. And the coupling is determined by physical parameters at extremality, thermodynamic parameters at extremality. The Schwarzian coupling is set by specific heat, or inverse specific heat. The gauge and rotation coupling are set by charge and rotation susceptibilities. A mode will contribute only if this susceptibilities are non-vanishing, or only if the scale is non-vanishing, the susceptibilities are finite. In the extremal BTC geometry, the solution rotates at the speed of light. The angular velocity is fixed to 1. This is one reason it doesn't super radiate. But it has a corollary. The susceptibility is infinite. Mode doesn't contribute. And in fact, this is good because we don't see it in our full space-time analysis. We only see one family of zero modes. So there is a fake zero mode in the near horizon. It doesn't uplift to the full space-time. So the answer is indeed just t to the 3 halves. And in fact, if you stare at it, formulas a bit more carefully, discarding this rotational zero mode is actually correct. In fact, it even predicts the right log S naught coefficient that Ashok computed in one of his papers. There's a consequence to this, which we are checking right now. Just as with BTZ, the 4-dimensional asymptotically flat Rice and Nordstrom also has infinite charge susceptibility. Its chemical potential is frozen, independent of charge. Okay, so we think that the zero mode, the gauge zero mode, won't lift to the full geometry, and it won't sort of contribute to the one loop determinant. But this is not something we have a firm evidence for. We have some need to check our numerics. Okay, so I'm going over time, but let me just wrap up by saying I've given you some examples of how the zero modes uplift to the full space-time as off-shell light modes, and it clarifies certain issues for me in terms of what it does for the rotation and gauge zero modes. I'll just highlight that this result is robust to finite alpha prime corrections, as you can read from our paper from a few days ago. And I'll just end with a comment that inspired Shiraz to ask a question earlier, which is my calculation was done in the context of the Euclidean solution. We were studying actually off-shell modes. They're not the eigenfunctions of the quadratic fluctuation operator. There's this beautiful formula of the one loop determinant in terms of quasi-normal modes by Denef, Hartmann, and Sachdev. And how do these results arise from quasi-normal modes? So I do know an answer in the case of BTZ. Now, I would have argued that the BTZ does not have graviton quasi-normal modes because there are no physical gravitons. But you can sort of, I think as Justin and friends did, you can look at the gauge fixed formula, compute the quasi-normal modes for transverse traceless spin 2 fluctuations. However, to compute the determinant, you also have to compute the determinant of the transverse spin 1 fluctuations associated with the ghost modes. You take the ratio, almost everything cancels, you get the Virasoro vacuum character, which then reproduces the answer. So in some sense, the quasi-normal modes know about it, But I would say, at least in that example, is degenerate because most of the contribution is not coming from the quasi-normal modes. It's still only coming from boundary gravitons. Okay? So the question is what happens in higher dimensions, and that's something very interesting. With that, let me stop.
So my question concerns the zero mode that can't be expressed smoothly in harmonic gauge. So typically, I think if I open up, Wald or Hawking and Ellis or something, I would see some theorem that any solution to the, linearized graviton equations of motion can be put in harmonic gauge by solving some PDE. Do you have a sense of what goes wrong with that theorem in this case?
No, I mean, based on that theorem, I was happy a year ago to say that maybe the rotational zero mode doesn't exist in curve. But a priori, no one told us that any gauge should be good for all problems. I mean, when in particular, the kind of context I think where the theorem was really analyzed was fluctuations around vacuum, to talk about physical gravitons, whereas we are in some extreme regime of near extremal black holes, where it's plausible that people haven't thought this through, and we are seeing explicitly why it fails. It's not like we're just saying it fails. We know what elements are in the kernel of the operator, why the operator can't be inverted.
Questions?
No, not the fibration.
The non-trivial warping, the reduction down to JT like model is not justified.
Definitely not.
But nevertheless, the answer becomes.
Yeah. I mean, because the point is that what your answer basically says you're not allowing fluctuations of the warp factor. So the natural reduction would have been along the isometry, and you would have gotten some 3D model with an extra field.
But if you take your modes, the final answer is that in the near horizon region, you try to think of them in terms of a reduction anyway.
Yeah.
Keeping this warp factor.
Yeah.
Are they activating the warp factor that you might have naively fixed into it? Because it seems from the fact that you get a Schwarzschild that ansatz was probably not so wrong.
I mean, the fact that they don't activate the warp factor, but the fact they don't activate the warp factor doesn't justify the ansatz.
A posteriori, is that what happens? Because you have the full.
Yeah, so it doesn't activate that warp factor.
Maybe one could just try to understand that in terms of, you're looking at very low energy excitations, low temperature contributions to the determinant.
Yes.
And activating that warp factor away from the value.
That would need to be shown. It would need to be shown that they're actually capped and they don't contribute in a temperature dependent fashion. That's a missing element. Yes. I mean, my strategy was don't worry about it, just work in higher dimensions.
This is great.
Yeah.
But I'm just saying answer analysis
yes.
might suggest that.
Okay, if there are no further questions, then let's thank Mukund again.